Hello, this is Brother Cromar from the Math Department here at BYU, Idaho, and these videos will cover Lesson 6, which is dealing with sampling distributions as well as the central limit theorem and some from the law of large numbers. And so the outline for these videos will go as follows. We'll cover first the law of large numbers, then we'll deal with sampling distributions when the distribution of the population data or the original population or the parent population is not normally distributed. Then we'll deal with sampling distributions when the distribution of population data is normally distributed, or the parent population is normally distributed. And then I'll cover some key points. First of all, let's cover the law of large numbers. So the law of large numbers states that the greater amount of observations in our sample, the sample mean, x bar, draws closer to our population mean, mu. So if I take a sample of men throughout the United States, say take a sample of 200, and if I take a sample and get a sample mean with sample size of 200 versus say if I take a sample size of 2,000, then that 2,000 sample would likely have a more accurate estimate of the true population mean. Okay, so basically the larger our sample size, the closer that our x bar, our sample mean, will be to our population mean. Or you can look at it in terms of how you flip a coin. If, say for instance, as we flip a coin more and more, the proportion of heads will become closer and closer to 50%. If you look at this graph where the vertical axis represents the proportion of heads and the horizontal axis represents the number of tosses, if we say for instance we may start off with fewer heads or more heads, but in the end if we flip the coin more and more, it'll get closer to 50%. And that is an example of the law of large numbers. So the greater the sample size, the more accurate we'll become, and say our sample mean will become even closer to our true population mean. Okay? Now the sampling distribution when the distribution of population data or the parent population is not normally distributed. Now when we talk about sampling distributions, we'll talk about it in three different ways: the shape, the center, and the spread of a sampling distribution. The shape for the sampling distribution, if distribution of population data or the parent population is not normally distributed, the answer is it depends. And it depends on our sample size. And as our sample size n increases and becomes large, then the sampling distribution becomes approximately normal. And this is where we apply the central limit theorem. Okay? So if we have a sample size of, say, well, if you go to these graphs below, if this is our original population where it's right skewed, we may have a sample size of 5, and then here's the possible sample means we could get here. Versus, say, a sample size of 15, notice the spread of the possible sample means we can get gets smaller, and it starts to form more of a bell-shaped curve here, not quite. But then if we have a large enough sample size, say it could be 25, it could be more, say if we take a sample of 25, then we would have an even smaller spread of sample means, and then the distribution will be bell-shaped. Okay, so this is an example. As our sample size goes up, the shape of the distribution becomes approximately normal. The center, if the mean of the original population is mu, which is the true population mean, then the mean of the distribution of sample means is also mu. So the mean of the original population is equal to the mean of all possible sample means. The spread, if the standard deviation of a population is sigma, then the standard deviation of the distribution of sample means is sigma divided by the square root of n. Now sigma is what we use normally to describe the population standard deviation statistics. Now, but with the sampling distribution, the standard deviation is the original standard deviation divided by the square root of n. And so the standard deviation of the distribution of sampling means is smaller than the standard deviation of the population by a factor of 1 over the square root of n. So what I'd like to do is that I'd like to go through an example of this here. Suppose the mean internet usage time at BYU, Idaho is 10 hours with a standard deviation of 2 and the distribution is right skewed. Suppose a random sample of 50 students were surveyed concerning their internet usage, and a sample would be 50 would be considered large. What is the mean, the standard deviation, and the shape of the sampling distribution of the mean internet usage based on a sample of 50 students? Well, the mean of the sample means is equal to the mean of the original population, which is 10. But the standard deviation of the sampling distribution is equal to the original standard deviation of from the population divided by the square root of n. So here we take the standard deviation of the original population, which is 2, divided by the square root of our sample size, which is 50, and then we get a new standard deviation of 0.283. The shape, since we have a large enough sample size, it's considered large in this case, the shape of our sampling distribution will be bell-shaped. And so we'll continue with sampling distributions when the population data is not normally distributed in the next video.